Okay, so this leads directly to the root test. We're going to suppose that the limit as k tends to infinity of the kth root of the modulus of ak is equal to r. All right? What this means is given any epsilon greater than 0, there exists a capital N so large that the kth root of the modulus of ak minus r is less than epsilon whenever k is greater than capital N. All right? Now these are all real numbers. So I can rearrange this and say the kth root of the modulus of ak lies between r minus epsilon and r plus epsilon. All right? Now, clearly this is non-negative. All right? So what I'm going to say going forward will only strictly speaking be valid when all three sides of this inequality are non-negative. But if r was 0, of course, that would be negative. If r is 0, I'm just going to replace the left-hand side of the inequality with a 0 and put an equals underneath this. All right? So we're not going to worry about that. All right? Now, if all three sides of this inequality are positive, then that means that I can take this inequality to the kth power. All right? And now I can sum. This was valid whenever k was greater than capital N. So now I'm going to sum. And I've got this beautiful three-sided inequality. All right? Now, notice that I've written this in exactly the same form that we saw for Cauchy's convergence criterion. This is valid for every natural number p. All right? Now, if r is less than 1, then we can choose epsilon so small that r plus epsilon is still less than 1. Choose epsilon smaller than 1 minus r. For example, epsilon equals 1 minus r over 2. All right? In that case, this series is less than this series. And this series, being a geometric series with common ratio less than 1, is convergent. So that means that this series, less than that, since this one, we can make it as small as we like by increasing capital N, we can make that one even smaller. So this series converges. Notice that this is the sum of the modulus of AK. All right? What we would say is the sum of AK is absolutely convergent. It means it converges in absolute zero, or in absolute value. It converges in absolute value. All right? What if R is greater than 1? Then we can choose epsilon so small that R minus epsilon is still larger than 1. That means that the sum of the absolute values here is larger than a divergent geometric series. This can't be made less than epsilon because the series diverges. Since that's larger, it also can't be made less than epsilon. And that means that the absolute series diverges. So we would say the sum is absolutely divergent. Note, strangely, that does not mean that it's divergent. The sum, well, actually, if R is greater than 1, then the series will be divergent. All right? But it is possible for a series to be absolutely divergent and yet converge. We call that conditional convergence. All right? So if R is less than 1, absolutely convergent. If R is greater than 1, absolutely divergent. If R equals 1, look what we've got here. The geometric series on the left has a common ratio 1 minus epsilon. No matter how small epsilon is, 1 minus epsilon is still less than 1. So that means that this series is convergent. On the other hand, no matter how small epsilon is, 1 plus epsilon is always greater than 1. So the series on the right is always divergent. So our series of absolute values lies between an absolutely convergent and an absolutely divergent series, telling us absolutely nothing about the series itself. So, as we know from previous investigations, if r equals 1, the root test fails.